that's for today. All right, kind of starting the second half of calculus today. The first half of calculus. I told you this at the beginning, but I'll kind of reiterate it. So there's two parts of calculus. And what's that? No, actually, well, there's three parts then, if we're going to do it that way. But there's two main parts. There's first studying differentiation, which we've been doing for a million years now. And when you think about it, this will make a lot more sense now. It does involve a limit, but it involves subtraction and division. So the first whole part of this course is about very fancy subtraction followed by division. And we call that the derivative. The second half of the course, and it's not even half, we start on it and then you pick it up in Calc 2. And Calc 2 is all about this part. But we spend the last month or so of this class talking about the next part, which is the reverse of this. And we're going to spend some time today understanding that. We'll spend a lot of time understanding that they are reverses of each other. But this, and I'm just going to put this here until we get some notation, sums and products. So literally the reverse of what we had before. It's addition and multiplication. Let's understand why. Let's see why that is. And I think by the end of today, you'll have a sense of why that could be. So let's start with a nice example. I've got the velocity time t, so v of t equals the velocity in, let's say, meters per second of a particle, just whatever, a car, something. So I'm going to have this velocity graph. And we're going to start off simple, and we're going to try to build our way up to an intuitive understanding of this idea right here. Jasmine, how's the glare? Do you need a light? A little bit. Sorry, front row. You all right there, Sam?
Yep.
Okay, cool. You're adjusting. So let's say I've got some particle, and it's moving at 3 meters per second. Now this axis represents velocity. So I've got this thing moving at 3 meters per second. T is going to be in seconds. This is going to be meters per second on that. And I go for 10 seconds. So I'm traveling at 3 meters per second constantly. That's a constant velocity. Do we all see that? Is that feeling right? When I say the velocity never changes, this is a weird thing. We must have captured this in the middle of something, because you can't just go from no velocity to this kind of velocity, right? You have to build up to it. So this is a bit of a weird situation. We're just looking at a moment in time for this thing. How far does it travel in the 10 seconds? Like I said, we're starting out chill. Somebody help me with that. Traveling 3 meters per second. What is it?
A little over 3.
So how are you getting your answer, Sam? Tell me your thought process.
10 divided by, take 10 seconds divided by 3.
Let me ask you this. If I was driving at 60 miles an hour for 2 hours, how far have I traveled?
Oh, I'm doing the opposite.
That's okay, that's okay. I want to give you something you're used to.
Yeah.
So what would be the answer to that? 60 miles an hour for 2 hours gets you how far?
120.
120 multiplying together.
So it's 30.
So here it's going to be 30. Traveling at 3 meters per second, constant, times the 10 seconds. Notice how the units cancel, and that gets me 30 meters. So we can do this algebraically, we can kind of do it intuitively, just thinking about car velocities and travel time. But a new way that I want you to look at this is that is also the area of this rectangle. So the area of this rectangle equals 3 times 10 equals 30. So even though we don't have to think about it as area, by doing so, we're going to gain a really deep insight into making this a little bit more general. So let's take a look at a slightly more complicated situation. So let's say it's somewhat more realistic. Let's say over the 10 seconds, so again, we've got 10 seconds worth of travel, and this is going to be velocity in meters per second. But I start off not moving at all, 0 is my velocity. And then I press on the pedal and start moving forward. And by the end of the time, I'm up here. Now let's say that the height on that is, let's say 3 meters per second as well. So really different behaviors. This one seems a little bit more realistic than this one. And let's estimate. Let's come at this in the same ways we did the first example to try to figure out an approximation for how far have we traveled. So how far have we traveled in the 10 seconds? So you might say, it's the area under the triangle. You'd be right. But you probably can't explain why that's so. So let's get at it. The answer is going to be the area underneath here. But let's think about it in a more procedural way. So here's the 5-second mark right here. And what we're going to do is think about how easy it was to figure out the distance I traveled if it was a constant velocity. Because then I just have the area of a rectangle. And approximate this thing with 2 steps. So let's say that this right here is representative of my velocity through the whole thing. So what I'm going to do is I'm going to use this rectangle right here, and notice that at 5 seconds, the velocity, what is the velocity at 5 seconds?
1.5.
Yes, 1.5, halfway through. That looks like a perfect triangle. So equals 1.5 meters per second. So in some ways I could say, you know, I kind of traveled at 1.5 meters per second the first part of this trip. So this is an approximate velocity for t between 0 and 5 seconds. Now I'm getting worked up. I'm going to do the same thing here. I'm going to say, okay, what was my final velocity? And it was 3 meters per second. And I'm going to say, all right, well, let's just use that as a representative of this first one, of this last half of the trip. So here, let's see, this was, yeah, I'll just leave that go like that. So this guy right here, what's the area of that rectangle? $15. Yep, so take the base, 5 seconds, times the height that we're using to represent that whole segment of travel, and that was 3 meters per second. So this area right here is going to be 3 times 5. Let's actually put this, I will write these in here. The area of this is 3 meters per second times 5 seconds equals 15 meters. So I traveled approximately 15 meters in that little time window. Let's come back over here. The area here was what was it? Well, we didn't actually find it. What is the area of this guy? 5 seconds. We're using 1.5 as the height. 7.5? 7.5, yeah. So this guy right here is 7.5 meters. So the total trip is approximately this estimate plus this estimate. So approximate distance traveled equals 7.5 meters plus this 15 meters, and that looks like 22.5 meters. Is that a pretty good estimate, you think? Is it over or under the truth? What do you think, Leo?
Over.
Yeah, and why?
We're adding also all the things on the left of the line.
Yeah, absolutely. I mean, your velocity in this little window wasn't always 3 meters per second. And your velocity here was certainly not always 1.5 meters per second. So this is an overestimate. Let's do this a little differently, and let's be kind of more conservative in our estimates. So if I take that same scenario again, I'm going to draw the same graph. There's 10 seconds. There's 3 meters per second. And I'm just drawing that so that I can make that guy right there. Here's 5 seconds. Notice how here we used our final velocity at the end of the window as the whole velocity for the whole time. There's no reason to use that over the starting velocity. So here I'm starting at no meters per second. Why is that less valuable than the final one? This one's way over. Let's look at this first one here. So in this window, so now let's use 0 meters per second. That's your starting velocity as representative. And that word representative is really a very technical word. And we will get into it next week a lot deeper. It's representative of the whole travel time. And that is from 0 to 5 seconds. T between 0 and 5. So when I do that, I don't even have a rectangle. It's basically saying I didn't move. The height of this rectangle is 0 meters per second. What's its area? 0. Height times width. So this thing has an area, let's just put a little note here, area equals 0. That's kind of saying I didn't travel at all, which we obviously know is false, but we also didn't travel at max speed over that first interval either. Now I'm going to do the same thing here. I'm going to use the left end, how I come into this interval, as the estimate for all of it. And we already know that this is 1.5 right here. Sam gave us that, I think. So let's say for this second window, we're going to use 1.5 as our estimate. So for t between 0 and 10, 5 and 10, use 1.5 meters per second as representative velocity. What is the area of this guy? 7.5. So here the area is 7.5, and it's meters. So notice how we're treating the velocity as constant on a smaller window than the whole thing. That's the name of the game for the rest of the semester, essentially. We're going to refine this as we move forward, but for now, what we've got is an area of 0 plus an area of 7.5. Traveled 0, traveled 7.5. So our approximate distance equals 0 meters plus 7.5 meters, and that's just 7.5 meters. Is that an overestimate, underestimate, or spot on? Under. That is underestimate. Any idea how I could maybe take that overestimate and this underestimate and come up with a better estimate? Average. We could just right now take the average of these two. So since both estimates are poor, very poor, let's average them. And I'm doing this because one is over and one is under. So the first estimate was 22.5. So we're gonna take our distance will be approximately 1/2 of the first distance, 22.5, plus the second distance, 7.5. Notice how that's a beautiful 30, and I get 15 meters. What's the area of this original triangle? 15. So notice how that's exactly the area of that first triangle, which is kind of cool. So let's put a note here, note with an exclamation point. This is precisely the area under the original curve. And I'm saying curve even though it's a straight line, the original velocity curve. Let's just draw a quickie here. We got 3, we got 10, I've got a triangle. And Joshua, how do you get the area of a triangle? 1/2 base times height, exactly. So this is 10, this is 3, that's a right angle. Area is 1/2 base times height. So here the area is 15. We're just lucking out, honestly. In general, you could do this averaging process. It's only working out perfect just because that's a triangle at the beginning. Let's do this one other way here. Let's see if we can get a better estimate. Any idea how I could get a better estimate just using,
Use the middle point instead of the starter and point.
Ooh, I like that. That's a cool plan. So break this in half, and instead of using either the starting velocity or the final velocity, use the velocity right in the middle as the representative velocity. That's a great plan. That wasn't where I was going, but that's a great idea. Let's do it. I like it. So instead of using the left or right velocity as a representative, let's use the middle velocity of each, and I'm putting some fancy terms in here, sub-interval. And the two sub-intervals are 0 to 5 and 5 to 10. Those are our two sub-intervals. So we'll come over here, I'm gonna make my triangle again, drop that straight down. That's 10 seconds. That's 3 meters per second. And we're gonna cut this sucker right in half, 5 seconds. So now I'm gonna make a rectangle here, but its height is gonna be the height of that triangle right in the middle. So at 2.5, I'm gonna sample the velocity at t equals 2.5 seconds. What is that velocity?
0.75.
What was it?
0.75.
How'd you get that?
Well, if we take the other one, what was
This guy
at
here?
5 seconds, it was 1.5. We divide that subsection to 2.5. We also divide the height by 2, and you get
Beautifully
1.5
explained,
divided
Leo.
by 2.
Absolutely. So is everybody seeing what Leo's saying? That if I grab this middle point, it's gonna be the halfway here and the halfway here. So it's 0.75. So right here, the halfway is 0.75 meters per second. And then let's just get the other rectangle right here. This guy's at 7.5 seconds. You think we should, what's the height there?
2.25.
2.25. And what I think Leo's doing is he's taking this height here and this height here and averaging them. Or how, is that how you did it roughly? Or should you do it
That
different?
or the other subsection plus the middle.
Oh, nice. Yeah, because same, you can translate that over. Yeah, exactly. So he's adding 0.75 change in height to this height right here, which is 1.5 plus 0.75, and then that gets you this guy right here of 2.25. So 2.25 meters per sec is that rectangle. And we're gonna add up those areas. Could you please do that and tell me what you get? Find the area of those two rectangles, pretty chill, and let's get an estimate for how far we've traveled. I'll try to get an app up here. We're gonna need it in a minute. Maybe I'm not good enough to get my password. That's all right. But I have my iPad today. Look at that shit. Look at that. Come on, USB-C. So height here, let's see how we do that. We did the height first, 0.75 times the width, 5. And then here we're using 2.25 times 5. And I'm pretty dang sure that's 15. So we actually got the perfect answer here. Notice how this is the perfect compromise. Little bit over, little bit under, little bit over, little bit under, and they balance out perfectly. Sam, I'm seeing a furrowed brow. Let me go through it? Yes, please. Yes, sir. So, you're cool with these heights on the rectangles and how we got those? Or not? You want me to go through it?
Yes, please.
You got it. You sound good. Oh, good. So we cut this 10-second interval in half, 5 seconds, and instead of using the start or the end velocity as the whole representative of the whole, we're grabbing the one in the middle. And that's here at 2.5 seconds here.
Yeah, that's right.
Yeah, and the height of that line, just using kind of the slope or all triangle-y things, is 0.75. And then over here in the middle is 7.25 and 2.25. So when I go to get the area of this rectangle, it's gonna be the base, which is 5, right? That's the base of the whole thing, right?
Oh, that's what it is.
Yeah, yeah, does that make sense?
Yeah,
Times the height, and then this one was also 5.
yeah, that makes sense.
That's it, were you getting half that or something, or something?
Yeah, I did,
crazy?
okay, times 2.
Oh, that'll do it. Any other questions? Okay, let's push this forward because this is a rare circumstance that things are so beautiful like this. Let's take a look at a more interesting velocity curve. And that one is gonna look like this. And I'm gonna actually have a formula for this guy. So again, V of t will end at 3 meters per second. That'll be the final velocity. We'll run for 10 seconds. So get that little corner point, and then inside here, do your best to estimate a parabolic velocity curve. And let's get the exact formula for this. So this is V of t, oh good Lord, I'm writing much fancier math, is some multiple of x squared. It's basically your classic x squared parabola, kind of scaled a little bit. But we can figure out what this number is by just knowing what we need at the end. I know that I need V of 10 to equal 3. So I'm gonna plug that in and solve for A. So 10 equals A times 3 squared. In other words, A equals 10/9, which isn't very attractive, but it is what we have. So the curve here, the velocity formula, is 10/9 times the t squared. Notice that checks out at the t is 0, and it checks out when t is, wait. Did I fuck something up here? I got the t's backwards, yes, sorry. Yeah, that doesn't work at all. I'm glad I checked my work. I got the 3 and the 10 backwards. So this right here is A times 10 squared equals 3. Sorry about that. This is worse than I thought. A times 100 equals 3. So A equals 3/100ths. That works better. So this is 3/100ths t squared. And I'm happy to walk through that again if I need to. Pretty atrocious. Kind of wish I had different numbers, but this is the mess I made for us to live in. So I guess we're living here. Welcome to my shack. All right, so we're gonna play the same game. Because right now, even if you knew even if you're like, oh, I get it, it's always the area under the curve. What's the area under that curve? I don't know. We don't have a nice parabola formula. So this area under here is completely unknown to us. So we're gonna come at this naively, and we're gonna play our game again. I've got 5 seconds in the middle, and I'm gonna make a rectangle to approximate that. Actually, what I'm gonna do is go with Kyla's idea. So we're gonna break this in half. So step 1 is cut the interval 0 to 10 into 2 pieces. What I'm doing here is outlining for you the whole process that's gonna become much more generalized, but this is the process we'll go through. I'm gonna cut my interval, my horizontal interval, into pieces. Here it's only 2. So they're gonna be 0 to 5 and 5 to 10. Step 2 is I'm going to choose the middle point in each subinterval. So these are called subintervals. This word cut, let's get the fancy technical word for it, just mark it here. This is also going to be called a partition. Partition it. Partition, I think I got too many P's in there. Partition. So I partitioned that horizontal interval into 2 pieces. I grab the middle point of each. So that's going to be, let's call it, let's see here, T1 is 2.5 and T2 is going to be 7.5. So I'm just grabbing the middle point here, 2.5, that's T1, 7.5, that's T2. And I'm gonna make a rectangle on each of those using the height at that point. So here I go up to the curve and I make a little approximating rectangle of that height. And then over here I go up to the curve and I make an approximating rectangle of that height. Let me stop and let me know if I need to explain a little bit more. It's super important you understand this process. This process is the rest of the class. I mean, it'll get better than this, don't worry. You'd be like, holy shit, I'm not coming back if we're doing this every day. It'll be better. We'll make it better. So what is the height here of this first rectangle? How do I find that? Plug it in the function, right? So we're gonna use this beastly little function we've got here. So the height of this rectangle here, let's just put it here, v of 2.5 equals, and I'm definitely gonna need a calculator, friend, because it's 3/100 times 2.5 squared. And if someone could give us that to,
0.1875.
I'm sorry, say that again, Leo?
0.1875.
0.1875. Nice, that's even more precision than I wanted. That's beautiful, thank you. And then we're gonna take this one with a height of v of 7.5. And so that's 3/100 times 7.5 squared. And what do we get for that one? Should be 9 times this answer.
1.6875.
Thank you. Anybody else getting these numbers to like Sandy? All right, we got some democracy going on, good stuff. Not that I doubt you, Sandy, but you know.
I was questioning my own.
Yeah, it's good to check. All right, so this one is this height, this one is this height, and again, those are meters per second. Those are our approximate average times over these two intervals. So the area of these rectangles, total area, equals the base, or let's do the height, 0.1875, that's the height of the first rectangle, times 5, this is the base, 5 seconds, plus the second one, which is 1.6875, that's the height of rectangle 2, the second rectangle, times 5. You could just add these two numbers together and multiply by 5, the decimal numbers, but I will need help because I can't do any of that in my head. Did you get Sophia? Yeah, you did, okay. Good. Leo, you got a number? Not yet.
Yeah, give me a sec.
It's all good. Did you get a number, Joshua?
Yeah.
Okay, cool.
9.375.
9.375 looks pretty
That's what I
dang
was-
reasonable. 9.375 is what you said, Eddie? Okay, cool. Anybody else getting, we got some, all right, we got it. Democracy says that this is approximately how far we've traveled in that time. Very loose approximation. Hard to say if it's over or under. Kind of looks maybe a little under because this area right here looks a little bigger than this one, and this one looks a little bigger than this one. So I guess that's actually under. It's probably a little bit under, yeah. What could I do to make this better? We've kind of used the best idea that we had so far. What could we do to get a better approximation?
Cut into one interval.
Yeah, let's use better rectangles, more rectangles, and refine this sucker. So a way to improve the estimate is to use more rectangles. Let's make that formal here. To improve the estimate, we use more rectangles. So just a quick re-envisioning of this whole thing. That was 10, that was 3, this was our velocity, this was our time. And then we had 5, and then we had 2.5. I don't know that we're gonna do this together right now because it's starting to get a little intense. Maybe it wouldn't be too bad. Maybe we could do one more, just one more. So what we're gonna do though is a slightly different way. I'll make your life easier. So what we've got now is cut 0 to 10 into 4 intervals. And they're all equal here. They don't always have to be, but they are for us right now. So I've got these four guys here. Now I just gotta figure out who I'm using for where I'm going to base the height of each rectangle. Because I need four rectangles here to easily compute that estimate. Let's just use the right end. If I use the right end, what do you think it's gonna look something like this. Is this gonna be an overestimate or an underestimate? That's definitely gonna be an overestimate, but it'll also be a little easier on the calculator keys. So let's just do it anyway. Just kind of see how it compares to that one right there. So let's use the right endpoint of each subinterval for our representative. And we've actually done a lot of this work, which is kind of why I thought we'd just go with it. Because we know the height of the curve at 2.5, we know it at 5, we know it at each of these actual points here. So let's go ahead and write above that here the height is what? What was the height at 2.5? It was 0.1875. 0.1875. So what I'm putting here are the heights at the right endpoint. And then at 5, let's see, what was that guy? Maybe we didn't do 3.75? Awesome, thanks. So at 5 is 3.75. And again, what Addie did to get that was she plugged in 5 into the formula for V, so that's V of 5. Next one's V of 7.5. And the last one's V of 10. And I think we got the 7.5 right down there. It was 1.6875. So this is 1.6875. And then V of 10, we already know is 3. So we're good. So can you figure out, please, for me, the estimate while I try to get my iPad rolling here with Desmos, because we're gonna make this sucker just so beautiful. And I've gotta move quickly because I've got 12%. I'm gonna charge this sucker while we're finishing this problem up. Just give me a little bit extra juice, because I can't apparently. This is not USB that charges, apparently. What's that charge? Yeah, it does. I think it is. Okay, I think we're good. What are you saying, Sam?
Oh, I thought you put that one, never mind.
Yeah, no, I think we're charging. It doesn't look like it because the power's going down, of course, because Regis. Let's just charge it properly. There. Good. Okay, so what do we got here? We are going to have 3 add up the area of the 4 rectangles. And I'm gonna write that sum out here. It's going to be 0.1875 times 2.5. The base of our rectangles has become smaller. Plus, the next one is 3.75 times the base, again, is just.
Isn't it just?
0.75?
Yeah.
I'm sorry, what did I get wrong?
Isn't it just the height of the side, not 3.75?
Oh, is that what it was? Was it just 0.75?
Yeah.
Yeah.
Oh, I thought I heard 3 in there. Yeah, thanks.
Height is 5.
Yeah, why would it be taller? That's a good freaking question. Thanks. That makes life better. Thanks, friends. 0.75, and then plus times 2.5. Plus 1.6875 times 2.5, plus 3 times 2.5. Now, one fast way to do this would be to add up all the heights, multiply by 2.5. But I'm sure you got it all done now. Can somebody give me a total? Starting to lose my grip here. I don't wanna.
14.
Thank you. Oh, it's okay. What was that? So
14.0625.
14.0625. Anybody else got that number? Yes. Wonderful. Thank you. Cool. Meters. And that's our approximate distance. And that's over the true value. Clearly over the true value. So now, how are we going to get the true value? Well, more rectangles. So how about, we're not going to do it, don't worry, don't get stressed. But if I made 8 rectangles and cut these each in half, that would be better. Or how about 16 or 32 or 64? How about 10,000 rectangles in there? Can you imagine what this would look like? Let's say I had just 1,000 rectangles in there. Think about what this would look like. It would essentially be about as close as we could get to it. So if I get enough rectangles in there, it's going to be super close to the truth. And if I could have infinitely many rectangles, it would be the perfect truth. And that's what the calculus part is all about. So what we're going to do is we're going to talk over the next month that we have together about how to take this process and create an infinite number of rectangles, find the area of the total area that they have, and we're going to do it all without this. We're going to do it all with a move like this. So let me show you how actually easy this is, and then we'll move to the Desmos really quick. Here's what we'll do next week when we get back together. I'm going to take that curve up there, or that formula. I've got 3/100ths t cubed. And I'm going to do what's called take the antiderivative. And I'll make all this. This is not the lesson about it. It's just enticing you into seeing how great this will become. And I'm going to bump the t cubed up to, oh, sorry, this should be t squared. I'm going to bump the t squared up to t cubed. I'm going to divide the front by my new exponent 3, and I get that. I'm going to take this, notice that, what is the derivative of this thing? That thing right here, that's why I called it the antiderivative. So I'm going to take the derivative backwards. I'm going to take that guy there, and I'm going to find this, evaluate at the right end, and I'm going to subtract what it is at the left end, and evaluate at the left end. And so that's going to equal 1/100ths times 3 cubed, 10 cubed, minus 1/100th times the left end, which is just 0 cubed. And look at what this turns into. This turns into 10, if you work all that out. And I could say that the true distance I traveled is 10 meters. We're way over. But that's how easy this process will become. All your calc skills from the first part, you're just going to do them backwards, which takes a little bit of practice. And then you're going to use what's called the fundamental theorem of calculus. And we'll get into all this. Again, this is not the official, this is the hinting of the official. Fundamental theorem of calculus. Calculus. There's 2 parts to it, and they link together this process with derivatives. And that's all going to come forward. And then we'll spend the rest of our time doing this the easy way. But first we pay a bit of a price on the whole thing. So let me get my Desmos example up here for you. Because I want to show you how that actually is the truth. What I said there, that if we had infinitely many rectangles, we would get 10 meters. So let's check it out. And this is cool. That sounds good. That sounds promising. Okay, I got 18%. Could do something here. Oh my God, it worked. Amazing, amazing, it worked, I can't believe it. I really can't believe it. So that's not our curve. Let me get our curve entered. You see how it's doing rectangle-y stuff? That's the stuff we've been doing. But we're gonna make a much less insane looking function. We're just gonna put in 3 100ths. And instead of t, I'm gonna use x, but same thing, x squared. And then our interval is going to start at 0, and it's going to run to 10. And then this n right here is the number of rectangles. Now let's put it up to 4 rectangles like we just did for a second. Let me get this thing down. And you see here that they're actually using the left endpoint for each rectangle. Can you see that? How here the height is based on the left end, here the height is based on the left, left, and left. Let's change it to be what we actually have. So right end, I want the left endpoint. I think, how do we make this thing do the left endpoint? Ah, here. I think it's c equals minus 1. There we go. That doesn't look right at all. I shouldn't have touched that button. Oh, there we go. Okay, there we go. There's the right endpoint. So that looks like our estimate, and we should get a number down here. Oh, look at the number, 14.0625. That's exactly what we got. We did it. You see that number right there? Boom. So let's get a better approximation, and as we were just saying, that means more rectangles. So let's up the rectangles and keep an eye on that estimate, that 14.0625. Well, you can't. Let's crank it up to, what do we got there? 25 rectangles, and our estimate is, that is just something really bad just happened. What just happened? Oh, I see. Thank you. Yes, my God. There we go. Come on, Wilfo. Why do you even let me tweak it like that? Why are you doing that to me? Bro. Here. 1. There we go. 10.608 is our new estimate if we use 25 rectangles. And so we can up that to, it looks like 100 rectangles, which is something you never want to do by hand. And our estimate is getting closer to the truth, but it's not at the truth, but it's hella close to 10. And if we were to do 1,000 rectangles, I don't even know if it could do that with the error not being so screwed up, but let's actually put in 1,000 and see what happens. And yeah, it's kind of choking a little bit. It's not used to such things. Actually, it didn't accept it at all, did it? Let's put 100. Oh wait, wrong. No. I'm screwing up. Oh, yeah. Okay. Well, anyway. Do you see? Sorry, this app is a little whack. Do you see where I'm getting at? That more rectangles gets us a better approximation. Infinite number of rectangles gets us the truth. Now, you've got a web work assignment. It's been a while, but we're not meeting on Friday. It's not due till Wednesday, so we could maybe work on it. Your web work assignment is going to be doing these sums for the left, using the right endpoint, using the left endpoint, and using the midpoint. But there's an app you can use. So in the web work, please be careful, look at the problems. There's an app that you link to, and it's a Desmos app that'll make this all easy for you. I could try to get us in there. Let's see, let me show you what I mean. Stop capitalizing it. What's your problem? What? It's like caps lock is permanently on here. What is that? What is that nonsense? Okay, let me just do this. And then delete the font T. Try that. Oh, okay, good. So it's homework 6. There's only 5 problems on there. And let's take a look at, let's see, problem 5. No, problem 4. Problem 3. Yeah, well, how about problem 1? I'm sure it's problem 2 if I'm gonna do 1 first. No, it's this one. Okay, so it's problem 1. Let's talk about how to do this problem. So you're going to use this Riemann sum calculator. These things that we are computing are called Riemann sums. They're basically the sums of rectangle areas. And we'll get into this deeply when we get back next Monday. But this calculator, let's click on it, starts with n equals 5. N is the number of rectangles that you have. So it's I guess it's essentially the same freaking app I basically was just using. So let's see how we would do this problem back here. So it says initially the calculator shows a left Riemann sum with subintervals for f of x is 2x plus 1. But they're asking us to update the function that we're using. So instead of that straight line, I come up here and put in x squared. What did it say? Plus 1? Is that right? Yeah. Yes, thank you. X squared plus 1. Put that in. You got your nice old parabola. You can zoom in and out. And there's a bunch of different questions you have to answer, which would be so painful if we had to do it by hand. The L is the sum of 5 rectangle areas using the left endpoint as the height. The M is for the midpoint, like Kyla suggested at the beginning, and the R is for the right endpoint. And here's how you tweak this. So let's do one of these. L is 5. So, oh wait, what was the interval actually too? Gotta make sure that's right. 1 to 4. See that there on the interval 1 to 4? Looks like we're not changing that. So A is 1, B is 4, and N is 5. To change the endpoint, C equals 0 is the midpoint. C equals minus 1, which I'm just going to type in, is the left. Nice and so roached. Doesn't it say? Oh, C equals, oh, okay. Actually, if I read the instructions, that would help, wouldn't it? So C equals 0 is the left endpoint. C equals 0.5 is the midpoint. And C equals 1 is the right endpoint. And so all you have to do is change these numbers and then get those sums. So for example, right endpoint with 5 sub-intervals is, and then where's my answer at? Oh, where are you seeing that answer? I'm sorry. Oh yeah, I see it right there in box 12. 28.68. So I come over here, and was I doing right? Is that what I was doing? Yep. So 28.68. Let's check myself. There. Check my answer. Hey, it liked it. So some of your assignment is that. The rest of the assignment is kind of doing this by hand, but you can check yourself with that app. Keep that app open. If you want, use that app to do all the problems. It shouldn't be too bad. How do you feel about this? Everybody feeling cool? Yeah? Should we call it? Or do you want to stay a little bit and work on this? I'll stay with anyone who wants to work on this and start on it. And if you don't, I'll see you when? Monday. Have a great Halloween. We all know how spooky. Cool. Be safe this weekend. We'll have a lot of fun. What's all this stuff, man? Neil, would you mind? sir?
Yeah.
Thank you.